Good morning, one and all. I am Dr. Kiran Kumar, working as Assistant Professor in the Department of Basic Science and Humanities, B.V. Radhakrishna Technology, Narsapur, Medak District. Today, I am going to teach a subject, Applied Physics, and the topic name is Semiconductor Physics. Nowadays, we are using mobile phones. We are enjoying the next level of luxury because of semiconductors. You can't imagine your life without a semiconductor. If you talk about time in terms of materials like bronze ages, copper ages, stone ages, like now we are in the ages of semiconductor. Semiconductor is the most preferred material nowadays. We are in the era of semiconductors. So this is the overview of today's presentation. First, I will introduce the semiconductors. Then what are the types of semiconducting materials, intrinsic semiconductors. So carrier concentration of intrinsic semiconductor and Fermi level is also important. So for intrinsic semiconductors, we have the derivations, means quantitative treatments. But extrinsic semiconductors like N-type semiconductor and P-type semiconductor, we don't have the derivations. Then finally, Hall effect and its applications. So semiconducting material. First of all, what is a semiconductor? So semiconductor is a material whose electrical properties lie between conductors and insulators. So semiconductors are playing a vital role in the field of electronics and communication. So most of the semiconductor devices like LED, photodiode, solar cell, rectifier, amplifier, right? These are all use semiconducting materials. So there are two different kinds of semiconductors, elemental semiconductors and compound semiconductors. Germanium and silicon are the elemental semiconductors. Gallium arsenide, indium phosphide are the compound semiconductors. So first of all, depending upon energy gap of the material, solids are classified into three types. Here, the energy gap is the main criteria to classify the solids into conductors, semiconductors and insulators. In case of insulators, the energy gap is large. The energy gap means energy difference between conduction band and valency band. Here, this is the conduction band. Conduction band is formed by a series of energy levels. The conduction band may be empty or partially filled, but conduction band should not be completely filled. If it is completely filled, there is no chance of mobility of charge carriers. Here it is contains series of energy levels. Here EC is the bottom of the conduction band. That is the lowest energy level of conduction band. EC is the lowest energy level of conduction band. Similarly, valency band. Valency band is formed by a series of energy levels which contains valence electrons. It is formed by a series of energy levels. That valency band may be partially filled or completely filled. It should not be empty. Here EV is highest energy level of the valency band, means top of the valency band. So the energy difference between EC and EV is known as energy gap of the material. So depending upon energy gap of the material, solids are classified into three types: insulators, semiconductors and conductors. In case of insulators, the band gap is large. The band gap is above 5 electron volt. Examples: glass, paper, plastic, wood, these are all insulating materials. Insulating materials are also very important as dielectric materials. And the semiconductors. In case of semiconductors, the energy gap Eg is small, around 1 electron volt. Germanium and silicon are the best examples of elemental semiconducting materials, semiconductors. In case of germanium, energy gap is 0.7 electron volt. In case of silicon, energy gap is 1.1 electron volt. So energy gap is the minimum energy required to excite electron from valence band to conduction band. So to make conduction, in case of germanium, 0.7 energy is the minimum energy required to excite electron from valence band to conduction band. And the last, conductors. Conductors are metals like copper, silver, gold. These are the best metals in the nature. Okay, in case of conductors, energy gap of the material Eg is equals to 0, which means the valency band and conduction band both are overlapped with each other. Hence, energy gap of the material is 0. So, among all the materials, semiconductors are playing a vital role in the field of electronics and communication. The reason is, in case of insulators, conductivity is not at all possible. Conductivity is not possible. In case of conductors, conductivity cannot be controlled. In case of insulators, conductivity is not possible. Let us say, if 5 electron volt is the energy gap, If you provide that much energy, then the material will be destroyed, but conductivity is not at all possible. In case of conductors, conductivity is constant. Conductivity cannot be controlled using in conductors. Even if you increase the temperature, conductivity of a conductor decreases. But semiconductors, conductivity can be controlled in two different ways. One is using impurities, the second one is using temperature. As temperature increases, conductivity also increases in semiconductors. And doping. What is doping? Doping is a process of adding impurities. So by increasing the doping also, conductivity can be increased. And the very important is the concept of hole. Here hole is a deficiency of an electron or absence of electron. The holes are possible in semiconductors only. Holes are not possible in insulators and holes are not possible in conductors. Holes are possible in only semiconductors. So the concept of hole is very important for making p-type and n-type semiconductors. So using p-type and n-type semiconductors, so we have different devices can be constructed like diode, triode, tetrode and so on. Diode can have the different applications like solar cell, LED, photodiode, rectifier. It can be act as a switch also. So the diode has many applications. Triode also very important in terms of amplifier. So mostly semiconductors are very important for electronics and communication engineering applications. So this is the base to classify the solids into insulators, semiconductors and conductors. Then we'll discuss the types of semiconductors. So what is a semiconductor? Semiconductor is a material whose electrical properties lie between conductors and insulators. The semiconductors can be classified into two types basically, intrinsic semiconductors and extrinsic semiconductors. An intrinsic semiconductor is a pure semiconductor. An intrinsic semiconductor is a pure semiconductor which does not have any kind of impurities. At 0 Kelvin, it behaves like an insulator. It behaves like an insulator. At higher temperature, it behaves like a conductor. So an intrinsic semiconductor is a pure semiconductor which does not have any kind of impurities. Next, extrinsic semiconductors. Extrinsic semiconductors are formed by the doping. So doping is the process of adding impurities. So the extrinsic semiconductors are classified into two types. What is doping? Doping is a process of impurity, means impurity atom means a different kind of atom. For every 10 to the power of 6 to 10 to the power of 8 atoms, we add one impurity atom. So the process of adding impurities is known as doping. So extrinsic semiconductors are formed by the doping. Extrinsic semiconductors are classified into two types, n-type semiconductor and p-type semiconductor. What is n-type semiconductor? When an intrinsic semiconductor like germanium and silicon. Germanium and silicon are the intrinsic semiconductors. Both are tetravalent elements. Both are tetravalent elements. Means their valency is 4. If you see the structure, of germanium, so covalent bond is present in the germanium structure. So to form 4 covalent bonds, so each germanium atom share 4 electrons. So basically it is a tetravalent element, valency is 4. So what is n-type semiconductor? An n-type semiconductor is formed when an intrinsic semiconductor is doped with a pentavalent impurity. Penta means 5. Means we are doping an intrinsic semiconductor. We are adding a pentavalent impurity, means 4 electrons form 4 covalent bonds. There is an excess of electron in n-type semiconductor. Those electrons lie in energy level known as donor energy level. Okay, so in n-type semiconductor, electrons are the majority charge carriers and holes are the minority charge carriers. Just we are doping with a pentavalent impurity. We are right. How can you define n-type semiconductor? When an intrinsic semiconductor like germanium or silicon is doped with a pentavalent impurity, phosphorus, arsenic, right? Then the resultant semiconductor is known as n-type semiconductor. In n-type semiconductor, electrons are the majority charge carriers and holes are the minority charge carriers. Next, p-type semiconductor. What is a p-type semiconductor? When an intrinsic semiconductor is doped with a trivalent impurity. Tri means 3. So we are doping with a trivalent impurity. So there is a deficiency of electron, absence of electron, which creates a localized, positively charged localized region. That deficiency of electron is termed as a hole. So in p-type semiconductor, holes are the majority charge carriers and electrons are the minority charge carriers. N-type semiconductors are known as electron donors, which semiconductor has excess of electrons, it can donate the electrons readily. Whereas p-type semiconductors are known as electron acceptors. There is a deficiency of electron, it is ready to accept the electrons. Both are very, very important for forming a p-n junction. Next, we will discuss about intrinsic semiconductor in detail. So in case of intrinsic semiconductor, we have to derive the expression for carrier concentration of intrinsic semiconductor. What is carrier concentration? The number of charge carriers per unit volume is known as carrier concentration. In intrinsic semiconductor, density of electrons in conduction band is equals to density of holes in the valence band. To understand this better, I will explain electron hole pair generation. What is electron hole pair generation? When energy is provided to a semiconductor, an electron gets excited from valence band to conduction band. In this process, an electron is generated in the conduction band and a hole is generated in the valency band. If two electrons take the transition from valency band to conduction band, two holes are generated in the valency band. Simultaneously, two electrons are generated in the conduction band. If n number of electrons excite from valence band to conduction band, n number of holes are generated in the valence band, n number of electrons in the conduction band. Means if P is the density of holes in the valence band and n is the density of electrons in the conduction band, in intrinsic semiconductor, n is equals to P, where n is density of electrons in the conduction band and P is the density of holes in the valence band. In intrinsic semiconductor, at any temperature, the density of electrons in the conduction band is equals to density of holes in the valence band. So using law of mass action, first we have to derive the expression for density of electrons in the conduction band and density of holes in the valence band. Using law of mass action, Ni square is equals to N into P. Means square of carrier concentration of intrinsic semiconductor is the product of density of electrons in conduction band and density of holes in the valence band. From this, we will calculate the carrier concentration of intrinsic semiconductor, which means to derive the carrier concentration of intrinsic semiconductor, two derivations are mandatory. We have to derive the two expressions. One expression for density of electrons in conduction band. One expression for density of electrons in conduction band. The second expression is for density of holes in the valence band, and using law of mass action, Ni square is equals to N into P, will derive the expression for carrier concentration of intrinsic semiconductor. So first let us start the first derivation, that is density of electrons in the conduction band. So this is the first derivation, density of electrons in the conduction band. So how can we derive the expression for density of electrons in conduction band? Here we need to take two different expressions. One is density of energy states, that is denoted by Z of E into dE. This is the density of states. And the second one is Fermi function f of e. So Z of e into d is the density of energy states, which gives the available energy states or electrons occupation, and f of e gives the Fermi-Dirac distribution function, which gives the probability of electrons occupation. And when the total states multiplied with the probability, that gives the number of electrons in the conduction band. So we are going to derive the number of electrons per unit volume in the conduction band, that is density of electrons in the conduction band, this derivation. For this, let Dn be the number of electrons available in the energy interval E and E plus dE in the conduction band. Then the Dn is equals to Z of E into dE into f of E. This Z of E into dE is the density of states, and f of E is the Fermi-Dirac distribution function. Means we are multiplying the total number of available energy states with the electrons occupation, probability of electrons occupation, then it gives Dn in the energy interval E and E plus dE only. But we need n. We have to derive the expression for n. Means we have to integrate this function from EC to infinity. Why EC to infinity? We are deriving this expression in the conduction band. Here EC is bottom of the conduction band. Here EC is bottom of the conduction band, and why the lower limit is EC and why the upper limit is infinity? We will take infinity here, the top of the valence band. Why that infinity? Means we are assuming that the probability of electrons occupation reduces to 0 at infinity. The probability of electrons occupation means f of e reduces to 0. F of e reduces to 0 to infinity only. So the lower limit will be EC and the upper limit will be infinity. So we'll start the derivation now. First n is equals to integral EC to infinity Z of e f of e into d. But we have to integrate this. Here this is a conduction band and this is the valence band. Here EC is bottom of the conduction band and EV is top of the valence band. So we are deriving the expression in the conduction band. EC is bottom of the conduction band and the upper limit will be top of the valence, top of the conduction band. But we are assuming that the probability of electrons occupation reduces to 0 at infinity only. So we are taking upper limit as infinity. So first we will take the expression for density of energy states. So Z of E into dE, the density of energy states is equals to 4 pi by h cube 2m to the power of 3 by 2 e to the power of 1 by 2 dE. This is the density of energy states expression. This expression has been taken from statistical mechanics. The density of energy states gives the available energy states for electrons occupation. Here m is mass and E is energy. Here we have to make two changes for this expression, since when an electron moves in a periodic potential, the solution of when an electron moves in a periodic potential, mass of electron is not a constant. Mass of electron varies with velocity. That variable mass is known as effective mass of electron. It is denoted by me star. Means we have to replace m by me star, and here E is energy. But we are deriving density of electrons in the conduction band, so we are starting at EC. And since EC, all the energy levels have to be neglected, which means E has to be replaced by E minus EC. So we have to make two changes. That is Z of E into dE is equals to 4 pi by h cube. Let us take this is 1. 4 pi by h cube 2 me star to the power of 3 by 2. Why me star? Electron possess effective mass in case of periodic potential. So m has to be replaced by me star. So m here, m is replaced by me star. Then E is replaced by E minus EC to the power of 1 by 2 d. Since E starts from bottom of the conduction band. Let us take this is 2. Equation number 2. Next we will take the Fermi-Dirac distribution function f of E. Let this Fermi-Dirac distribution function is also taken from the statistical mechanics. The Fermi-Dirac distribution function f of e is equals to 1 by 1 plus exponential of e minus ef by kt. Here E is energy, f of E is a Fermi-Dirac distribution function which gives the probability of electrons occupation, and the value of f of E varies from 0 to 1. If f of E is equals to 1, there is a 100% probability of electrons occupation. If f of E is equals to 0, there is 0% probability for electrons occupation. If f of E is equals to 1 by 2, there is a 50% probability for electrons occupation. Here f of E, here E is the energy, Ef is Fermi energy, K is the Boltzmann's constant. From this, for all possible temperatures, E minus Ef is much greater than Kt. Why E minus Ef is much greater than Kt? If we take an intensive semiconductor, the energy gap Eg is equals to around 1 electron volt. In case of germanium, it is 0.1 electron volt. In case of silicon, it is 1.1 electron volt. And most importantly, in intensive semiconductor, the Fermi level exists at the middle of conduction band and valency band, which means the Ef minus E is always less than 0.5 electron volt. Let us take 1 electron volt. E minus Ef is equals to 1 electron volt is equals to 1.6 into 10 to the power of minus 19 joules. But on the right hand side, we have a Boltzmann's constant. Boltzmann's constant value K is equals to 1.38 into 10 to the power of minus 23 joule. Means for all possible temperature, this E minus Ef is much greater than Kt. So from this we can write E minus Ef by Kt is much greater than 1. And if x is greater than 1, e power x is also greater than 1. Then exponential of E minus Ef by Kt is much greater than 1. If this is much, e power x is much greater than 1, then 1 can be neglected from this Fermi-Dirac distribution function. That is, f of e can be written as f of e is equals to 1 by exponential of E minus Ef by Kt. This is equals to exponential of Ef minus E by Kt. This is, let us take 3. Now we have to substitute 2 and 3 in equation number 1. Then n is equals to integral Ec to infinity. So 1 z of e into, I am writing 1. So z of e is equals to z of e into f of e into d. This is 1. Now I am writing equation number 2. This is 2 and 3. I am substituting 2 and 3 in 1. Then n is equals to Ec to infinity 4 pi by h cube 2 me star to the power of 3 by 2 E minus Ec to the power of 1 by 2 and a Fermi-Dirac distribution function exponential of Ef minus E by Kt into dE. Here this term 4 pi by h cube is a constant, 2 me star to the power of 3 by 2 is a constant, and in this term E power of Ef by Kt is a constant, since Fermi energy is a constant for a given system, and e to the power of x minus y can be written as e to the power of x into e to the power of minus y. Means the first term can be taken out. So constant term can be taken out. Then it can be written as n is equals to 4 pi by h cube 4 pi by h cube 2 me star to the power of 3 by 2 and exponential of Ef by Kt to integral Ec to infinity exponential of minus E by Kt into dE, and E minus Ec is also there. So E minus Ec to the power of 1 by 2 exponential of minus E by kt into dE. So to solve this integral, put E minus Ec is equals to Ex. Now differentiating on both sides, dE is equals to dx. From this, E is equals to Ex plus Ec. And if you see the limits, if you take the lower limit Ec, when lower limit Ec, here we substitute Ec is equals to Ec minus Ec is equals to 0. Then the lower limit will be 0. Now we will take the upper limit. Infinity minus Ec is equals to infinity minus something is infinity. Then the upper limit will be infinitive. So we will substitute here. Then n is equals to 4 pi by h cube to me star to the power of 3 by 2 exponential of ef by kt. The lower limit will be 0 and the upper limit will be infinity, and x to the power of 1 by 2. Then minus e is equals to minus x minus ec. Then we can write the exponential of minus x minus ec by kt into dx. Here also, in this term, Ec by kt is a constant that can also be taken out, and we write e power x into e power minus y is equals to e to the power of minus x minus y. So this term can be added here. Then n is equals to 4 pi by h cube 2 me star to the power of 3 by 2 exponential of ef minus ec by kt into 0 to infinity x power of 1 by 2 e to the power of minus x by kt into dx. Here this term can be done as e to the power of x minus y can be done as e to the power of x into e to the power of minus y, and this ec by kt can be taken out because it is a constant and the term added here. Right, so we can write like this. But such integrations cannot be solved like these integrations. Like if we solve 0 to infinity root x into e to the power of x dx, such type of integrations cannot be solved using UV method. Using a general solution like UV method, such type of integrations cannot be solved. We have to use a special function known as a gamma function. So using gamma function, using gamma function 0 to infinity x to the power of 1 by 2 x to the minus x by kt dx is equals to kt to the power of 3 by 2 pi to the power of 1 by 2 by 2. Let us take this is 4. Right? This is approximated using gamma function. That function is equals to kt to the power of 3 by 2 pi power of 1 by 2 by 2. So we are substituting here. Then density of electrons in conduction band can be written as 4 pi by h cube 2 me star to the power of 3 by 2 exponential of ef minus ec by kt. Next, kt to the power of 3 by 2 pi power of 1 by 2 by 2. Here 2 let's cancel. Here we have 2 me star to the power of 3 by 2. 2 me to the power 3 by 2. Here kt to the power of 3 by 2, and here we have pi power of 1 by 2 and pi. Pi power 1 into pi power of 1 by 2 can be done as pi power of 3 by 2. So we are adding all the terms. Then we can write as 2 into 2 pi me star kt can be written as 3 by 2, and h cube can be written as h square to the power of 3 by 2. So by h square to the power of 3 by 2 the exponential of ef minus ec by kt. So this is the expression for density of electrons in the conduction band. This is density of electrons in conduction band. It is really important for examination purpose. Like we have to derive one more expression for P, that is the density of holes in the valence band. So after deriving density of holes in the valence band, we have to use law of mass action. According to law of mass action, Ni square is equals to N into P. Right? So after deriving N and P, we will derive Ni using law of mass action N into P. That gives the carrier concentration of intrinsic semiconductor. So dear students, we will derive the second expression, that is density of holes in the valence band, in the next session. Okay, thank you for watching.
Like, share and subscribe. Hit the bell icon for more updates.